This is another important derivation in wave optics, the bandwidth or fringe width for interference pattern. So it's the double slit experiment. We have a main source slit which emit monochromatic light. This light passes through two slits S1 and S2 placed right after that. The distance from S to S1 is taken equal to S2 S2 in the normal case. There may be differences as shifted up or down, but general derivation as S1 is equal to SS2. So this light comes out and spread. They will interfere and form the pattern on the screen. So this is a screen kept at a distance capital D from the plane of the slits. The distance between S1 and S2 is D. One light ray from S1 reach P. P is any representative point on the screen. P can be the center, below, above, right, left, any representative general. So from S1 and S2, one light ray reach P. The slits are so small so that one light ray or light wave reach P. O is the center of the pattern, which is exactly in line, act as a perpendicular bisector to S1 and S2 passing through S. S1, S2 is small d. Just for the derivation purpose, this line is extended so that it meets at M and N. O to N and O to M both are equal. That's equal to half of d by 2 each. The distance to the point P from the center of the screen is measured as yn. Y because here we take y-axis vertical. N stands for nth band. This point may be a third or fourth bright or dark band can be formed. So yn represents center to nth band, can be bright or dark. S1, S2 act as coherent sources of light because both of them get same wavelength, and whatever light emerging out from S1 emerges out same type from S2 because it's originating from single monochromatic source. The point O, if you check S1 to O, S2 to O equal because on the perpendicular bisector. So the total path difference SS1 to O, SS2 to O is equal. Total path is equal SS1 O, SS2 O. So the path difference will be 0. So that they satisfy condition for constructive superposition and forms a bright band at O. The other points on the screen appear bright if the path difference is n lambda, where n is equal to 0, 1, 2, 3. And it appear dark if the path difference is 2n minus 1 lambda by 2, where n starts with 1, 2, 3. Now for the derivation purpose, we need to find the path difference between light from S to P. Since SS1 is equal to SS2 in this case, we need to find only path difference between S1P to S2 to P. So we take these two triangles, right triangles. For S2P, we take the triangle as 2MP so that hypotenuse square is base square, which is D square, plus altitude square, MP square. MP will be yn plus D by 2. Same way for triangle S1NP. S1P the whole square will be base square, which is D square plus NP square. NP will be yn minus D by 2. So S2MP will give you S2P square equal to D square plus yn plus D by 2 the whole square. Triangle S1NP will give you S1P square as D square plus yn minus D by 2 the whole square. We subtract S2P square minus S1P square. So using subtracting d square get cancelled. Now this is a plus b whole square minus a minus b whole square. So a square, b square get cancelled when you subtract. It will be just 4ab. So 4 into a is yn, b is d by 2. So opening the bracket as a square minus b square is a minus b into a plus b. This will be 4 into a into b. This get cancelled yn to 4 and 2. So it will be 2 yn b. The formula we used is 4ab for expansion of this. Now to find path difference S2p minus S1p, take S2p plus S1p to the right side. This is the general path difference delta, what we mentioned here. Now, normally the wavelength involved are very small. So if P is very close to O and S1 and S2 are very, very close in the order of millimeters or less than that. So S1P and S2P will be both approximately same, equal to B. If S1 and S2 are very close in the order of millimeters, this is shown large for understanding, and P is very close to O. That's a practical case. The distance from S1 to P, S2 to P with S1 S2 close is approximately equal to D for addition. It will be different, but you can take approximately same for when you add. It won't be much different. So you can take S2P plus S1P as 2D. Subtraction you can't take equal because really different. Additionally, you can approximate. If you take subtraction, that will be 0. The calculation stops here. The other one, even with a slight error, you can continue with the calculations. Now, the path difference S2P minus S1P, which is represented as a delta, is 2YND, or 2YND divided by S2P plus S1P become 2D. The 2 will go. You get delta from that. It's an important result used for a calculation between delta and Yn in the numerical scale. From that, you can find different cases for bright and dark, the path difference. If it's a bright band, the path difference will be n lambda. So you substitute delta as n lambda here. You get n lambda equal to yn d by d. From that, get yn. So yn will be dn lambda by d. So now for beta, find y1, y2 and subtract y2 minus y1. So y1 will be just d lambda by d, y2 will be 2 d lambda by d. This is the position of bright band. Between two bright band will be the width of the dark band. So width of the dark band is y2 for bright minus y1 for the bright. So 2 d lambda by d minus d lambda by d, that will come as d lambda by d. That's the width of the dark band. For width of bright band, we should go for position of the dark band. For dark, the condition is path difference equal to 2n minus 1 lambda by 2. So substitute this delta here. We'll get 2n minus 1 lambda by 2 is yn d by d. Get yn by putting d and d on the other side. So 2n minus 1 d lambda by 2d. Now we again find y1, y2, putting 1 will be 2 into 1, 1, 2 minus 1 is 1. So d lambda by 2d. Putting 2, 2 into 2, 4 minus 1, 3 d lambda by 2d. Now for the width of the bright band, it's a difference between the positions of two dark bands. So subtracting that, you get 3 d lambda by 2d minus d lambda by 2d. This will be 2 d lambda by 2d. The 2 get cancelled. We'll get just d lambda by d. That's the width of bright band. And it's seen both bands are of same width in interference. Now this is called linear width or fringe width or band width. There's something called angular width. It's an angle subtended by the interference pattern at the center of the coherent slits. At this point, what angle is subtended by the pattern? That will be the angular width. So we can use angle equal to arc length by radius. Arc length will be the beta and radius will be capital D. So angular width will be beta by capital D. Beta is already d lambda by d by d. D get cancelled. We get angular width is lambda by d. This is independent of capital D. It only depends on the wavelength and the distance between the two coherent slits. So this derivation, what we have done, the first part is for linear width. The second part is for angular width. D lambda by d is the linear width. This result is 2 times d lambda by d, that becomes just d lambda by d. 3d lambda minus d lambda will be 2d lambda by d, 2d, it becomes d lambda by d. This expression for linear width. It's even called fringe width or bandwidth.